So today I am here to present my seminar topic, quarter waveplate. So it is an optical device that converts the state of a polarized light. So we all know light is a transverse wave. So that means the light travels in all directions. That means an unpolarized light. So we need to polarize the light into a particular direction. So for that we use an optical device called quarter waveplate, and also half waveplate is there, that will be explained by Shilkit. So for what exactly we are using quarter waveplate? It is actually a bifringent crystal which introduces a phase difference of pi by 2 between the two components of light. So from this definition I will be explaining what is a bifringent crystal and what are the components of it. Because there are two perpendicular components of light. So I will be explaining now what is bifringent concept and the axis of the light. So bifringence. Birefringence is a property of crystal that, if considered this as a piece of crystal, so a plain polarized light is entering to the crystal. It will split the light into two. One will be ordinary ray, the other will be extraordinary ray. This usually takes place because of the difference in their speed. The light will be split into two, and one will be ordinary ray and other will be extraordinary because of the difference in the speed, and this causes a phase difference. And now about axes. Birefringent crystals have two special components. One is known as fast axis and other is slow axis. So consider this as a crystal. So if this is the fast axis and this is the slow axis, and they make a phase difference of pi by 2, which is 90 degrees. And why the axis is axis means crystal is actually anisotropic. That means it is not same in all directions. The light acts differently on different directions and at different speeds. So the fast axis, the light will move very fastly, and its slow axis will lag behind. And the delay difference will be pi by 2, that is 90 degrees. And the construction of quarter waveplate is made of thin birefringence, and the thickness is adjusted in a way to produce a phase difference of pi by 2. So we have to get a result of pi by 2, so the thickness is adjusted according to it. Now let's move to the working of quarter waveplate. So as I said, birefringent crystal, quarter waveplate is similar to that. If this is a quarter waveplate and light enters to it, it makes splits into two components. One along the fast axis and another along the slow axis. And what will be the output produced? Like if the input plain polarized light is making a degree of 45 degree with the axis, it will give circular polarized light. In quarter waveplate output, there are two outputs. One is circular polarized light and elliptical polarized light. So to get an output of circular polarized light, we have to give the input light should be perpendicular 45 degree with the axis. Axis is like fast axis. I can represent it in the board. The light should be 45 degree with this axis. In that way, we will get an output light. If theta is equal to 45 degree, we will get a circular plane polarized light. And if the output is other than 45 degree, for example, if it is 22.5 degree and all, we will get an output of elliptically polarized light. So, what is the difference means? In circular, the amplitude of the two axes will be same, and the amplitude of in this case will be different for fast axis and small axis. That's why here we get elliptical model and here we get circular. And now we are deriving the equation for the thickness of quarter wave plate. So there is an equation to know this equation of the phase difference reduced between legs. Two legs, that is 2 pi by lambda n e minus n naught t, where this represents the phase difference produced, and this is the wavelength, and ne is the refractive index of extraordinary light. And O will be the refractive index of ordinary light. So, as we know, the phase difference for a quarter wavelength is pi by 2. We can substitute this value to this equation. That is pi by 2 is equal to 2 pi by lambda n e minus n of t. So, we are going to find the thickness, right? So, we can take all this into this side. So, we get so from this we get an equation for thickness like T is equal to lambda by 4 ne minus no. This is the equation for thickness, to find the thickness of a quarter wave plate. So let's move to the applications. The quarter wave plate is usually used in optical instruments, microscopes, laser systems, and communication and reading glasses. So basically, we conclude that quarter wave plates is an important optical device that converts the plane polarized light into circular or elliptical polarized light using a wire fringes and phase difference. So that's all my topic, and the rest will be given by Shah.